Okay, so part 4 of Lab 20 is basically a nothing. It's just showing you how to set things up. So this DG403 chip, which I have here set up on the breadboard, is a pretty complicated animal. It requires ground plus 3 different power voltages. So for plus 5 volts, I'm using the VCC output of the EE board, which I've programmed to plus 5. And then we have minus 9 volts and plus 9 volts for the VP minus and VP plus. And then we have ground. So this thing is pretty tricky. So it's basically, it's 2 units, and each unit is a so-called double throw switch. I think it's Oh, I always get confused about whether it's single pull or single throw. Oh, I won't try to use the vocabulary just yet. So, okay, there's this digital input, input 1, 3. And if this thing is high, then source 1 and drain 1 are connected to one another with a low resistance. We'll see how low in just a minute. And if in 1, 3 is low, meaning 0 volts. High meant 5 volts. Low means 0 volts. If it's 0 volts, then this switch is open. So source 1 and drain 1 are disconnected from one another. They're connected by a very, very high resistance. So they're essentially an open circuit. So high is closed circuit, low is open circuit for S1, D1. For S3, D3, high is open circuit, low is closed circuit. Okay, so this connection is on if this input is low, this connection is on if this input is high. And low means 0 volts, high means 5 volts in our digital world here. And then I think it's analogous for this 2-4 pair. I think most of the time we'll use just this. So Tom has a note that says if you have an unused one of these CMOS logic inputs, so this 1, 3 or 2, 4, in other words, pin 15 or pin 10, be sure to either ground it or connect it to plus 5 volts so that it doesn't sit very close to V threshold and chatter on and off, and using a lot of power. So, so I wired this spare pin 10 here to ground. I'll show you, I'll give you a little tour in a minute. Okay, so what are we doing? That part 4 is just set up. So I guess I'll show you in a second how I set everything up. And then let's go on to part 5. So part 5, it's kind of dull. It's kind of like eat your spinach, but it's just to show you, was to ask the question, how good a switch is this analog switch? Oh, by the way, this DG403 thing, it is an analog switch. So it is an application of MOSFETs. The MOSFETs make very good switches. And most of the rest of this course, we will use MOSFETs as switches to turn digital logic signals on and off. But you can use a MOSFET switch as basically like a computer-controlled analog switch. Imagine you make or break a connection in one of your analog circuits. I'll give you one example of this. One example of this is, you know, we have the op-amp integrator. We have our op-amp integrator. Okay. And we said, okay, the output, you know, V out is minus 1 over RC integral of V in with respect to time. But then where do you start? And well, so we sometimes put a big resistor up top just so that DC effects don't accumulate. But another thing you can do is you put a switch. You say, okay, but who's going to flip the switch? Well, if you have an analog switch, you see, then you can have some external logic signal, like your computer can say, okay, I want to close the switch so that the output gets zeroed, and then I'll open the switch and I'll start integrating. So a computer-controlled switch is useful. And even in this case, it's a computer-controlled switch which is part of an analog circuit. Or, you know, maybe you want to like use one oscilloscope channel to measure 10 different things. So you want to be able to select between them. So you could do that with an analog switch. So anyway, so being able to use digital control, in other words, under the control of some kind of intelligent agent like a computer, to turn an analog connection, make or break an analog connection, is it has all kinds of applications. So that is the point of an analog switch. The point of an analog switch is to be able to use digital logic, in other words, programmable intelligence, to make or break a connection in an analog circuit. Okay, so the first example is we just have an input and we're just grounding that input. So basically, if the switch is closed, the input's connected to ground. If the switch is open, the input is disconnected, it's floating. And we're going to close it. So the switch will just be connecting to ground. You say, what in the world is the point of that? So we have this 1K resistor between our input signal and the switch. So basically, what this is asking is, what is the resistance? So remember, if you close a switch, then its resistance should be 0. Ideally, a closed switch should have a resistance of 0. So how ideal is it? So, there's basically this switch, when it is closed, looks like some very small resistance. So the question is, how small is it? And, so if we peek here with the oscilloscope, then what we will see is that the voltage we see with the scope is our input signal times the switch's closed resistance. I think he calls this R on, actually, divided by, well, it's this number, which is probably a pretty small number, plus 1 kilo ohm. So that is approximately just V in times R on divided by 1 kilo ohm, because we're going to assume that R on is much smaller than 1 kilo ohm. So let's see how that works. Oh, now the tour. Okay. So I connected my DG403. So if you connect it this way, you can see the little tab on the left-hand side. Okay. And also you can read, if you read the numbers appear readable when you connect it the proper way. Okay, so this is pin 1 on the left, the bottom left corner. Pin 16 on the top left corner. So D1 and S1 are pins 1 and 16. Okay. Those are the ones we're using in this first exercise. Pin 2 is a no connect. Pin 3 and 4 are D3 and S3. I guess D and S are drain and source because it's basically you're making this connection with a MOSFET. And then pins 5 and 6 are S4 and D4, which are the other half of the switch DG403 package. Pin 7 is a no connect. Pins 8 and 9 are D2 and S2. Pin 10 is the logic input that enables or disables switches 2 and 4. Okay, now we get to the interesting stuff. Oh, by the way, this unused pin 10, because we think we're not going to use this 2 and 4 very often, I grounded it down here. Okay, so this black wire is connecting that unused logic input to ground, because we know now, after seeing that mysterious behavior with the light bulb, that CMOS inputs behave very strangely when they're left floating. So you always want to connect a CMOS logic input affirmatively to 0 volts or your logic high voltage. So in this case, 0 volts or 5 volts. Here is pin 11. It's plus 9 volts, which I have up here, this red stripe up above. Then here is plus 5 volts, which I have up here, this blue stripe up above. And then here is ground, which is down here, this blue stripe down below. And then pin 14 is minus 9 volts, which I have down here, this red stripe down below. And then pin 15 is the logic input that tells switches 1 and 3 whether to be open or closed. And then pin 16 and 1 together are the two halves of this S1D1 switch. Okay, so then I have pin 1 grounded. Okay, so that's according to Tom's diagram here. And then I have pin 16 connected to an input signal through a 1K resistor. So here's pin 16. Here's my 1K resistor. And here's my input signal from the function generator. And I'm watching that with the scope channel 1. And then I'm watching the other side of the 1K resistor. So with scope channel 2, I'm watching pin 16, this S1, kind of source 1. So if this were an absolutely perfect switch, then I would always see 0 volts at pin 16 when the switch is closed. And the switch is closed because you see at pin 15, I use this blue wire to connect pin 15 up to plus 5 volts because this is basically a signal. It's like a logic input. So we're connecting it for the moment up to plus 5 so that the switch is closed. Okay, then let's look at the waveforms. So, first this is a power supply, so we need VCC is 5 volts, and then we have VP plus is 9 volts, VP minus is minus 9 volts. My waveform is a 1 kilohertz sine wave, 5 volts amplitude, 0 offset. So now, if we look with channel 1 of the scope, we see our 5 volt amplitude sine wave. If we look with channel 2 of the scope, we see a much smaller sine wave. It would be absolutely 0 if the switch, when closed, had 0 resistance. Let's see how big this is. So let's go to 100 millivolts per division. Well, actually, if we go to 50 millivolts per division, let's go to, okay, fine. Let's just stick with 100. So it seems like this ratio is, this ratio is 0.16 volts divided by 5 volts. Okay, so 0.16 volts divided by 5 volts equals R on divided by 1 kilo ohm. That's approximately true, would be exactly true if, well, I should say R on plus 1 kilo ohm, but that's a small effect. Okay, so divide by 5. So 0.016 divided by 0.5, that's like 0.032. Yeah, so 0.032. So I think R on is like 32 ohms. Okay, so seems like it's not 0, but it's a pretty small resistance. It's like, okay, a few tens of ohms. So that was this first. The thing is, how on is on. Okay, so on is like 30 ohms worth of on. And then the next thing, and again, these part 5 here, it's not super exciting. You're just saying how good a switch is the switch. Okay, for part 5.2, we removed the 1K resistor here, replaced it with a wire. So that is what happened here. This became a wire. And instead of the direct connection to ground at pin 1, we have a connection to ground through a 100K resistor. That's happening here. And then, so we're still monitoring the input signal that was to the left-hand side of this resistor. There's no resistor anymore. So let's move scope channel 2 over to pin 1. So it's looking at the top of this 100K resistor. And I think what we're supposed to be looking for, if the switch is closed, so this is 100K compared to like 30-ish ohms. So 30-ish ohms is tiny compared to 100K. So in other words, this resistance, this on resistance of this switch when it's closed, should be absolutely negligible compared to 100K. So this signal and this signal should be indistinguishable from each other on the scope when the switch is closed. And we can see that happen. So believe it or not, there are 2 traces overlaid here. So there is channel 1, there is channel 2, and you really can't tell them apart. So the idea is that And this is a 5-volt amplitude, so it's 10-volt peak-to-peak sine wave at 1 kilohertz. So the idea is, as long as the relevant resistances on the outside here are, huge compared to like this 30 ohm on resistance, then and then it looks like a good switch. Okay, there was one other thing we're supposed to notice here. Let me check that. Okay, yeah. So the next thing is, so that was how good is the switch when it's on. So when the switch is on, it should look like basically zero resistance. Okay, so now if the switch is off, and how do we turn this switch off? So the way we do that, right now we're doing it by hand. So we turn this switch off by taking pin 15 and connecting it to ground instead of +5. So here is, here's pin 15. It's this little wire. So let's connect that to ground instead of +5. Okay, so now the switch is off. Okay, so it should be an open circuit. So if I go back to our previous display, then you see it looks as if nothing gets through to this point. The blue curve there is just this flat line there. Now let's see if we can trick it. So nothing gets through DC, but let's see if anything gets through AC. So let's create some high frequency stuff. So first of all, let's take this sine wave and turn it into a square wave. Square waves have sharp edges. And actually, you can maybe see just a little bit. Well, actually, Tom says try a high frequency sine like 100 kilohertz. So, okay, let's do what Tom says. What the heck? Okay, so we'll take our sine wave and we'll try like 100 kilohertz sine wave. Okay, 100 kilohertz sine wave. And we'll go to a zoomed in time scale. Oh, look at that. You do see a little bit leak through. Okay, so there's 1 volt per division. So if we blow up this signal on this side by a factor of 10, so it looks like, there's a phase shift too. So phase shift kind of tells you, gee, this looks like a capacitive effect or a high pass. And also, not only is it a phase shift, it's a phase shift so the output is earlier than the input. So that is a symptom of high pass filtering. So it kind of makes sense. There's some kind of capacitive connection here. Okay, so the output is ahead of the input. So that's kind of a capacitive effect. So we see a little phase shift, and we see, well, that looks like, let's see, it would be 1 part in 5 maybe, so it's like 1 part in 50. So it's look like maybe 2% of the signal gets through, and there's a little bit of a phase shift. Okay, and then I think another thing that's cool is if we do a square wave. Let's see, square wave. Oh yeah, that is kind of cool. So then you kind of see, here, let me get channel 1 out of the way. Well, okay, I guess we'll just put channel 2 on top of it. So then you kind of see like the derivative of a square wave. And actually, I think if I make it a lower frequency square wave, that's more obvious. So let me try here's a 10 kilohertz square wave. Yeah, in fact, I could even make a 1 kilohertz square wave. See, but its edge is just as fast. 1 kilohertz square wave. And then let's zoom out a little bit in time. So we'll go to here 20 microseconds per division. Yeah. So actually, but you can't tell that it's a square. But you see the little spike, which is kind of like the derivative of the square. And if we we zoom out much more. Yeah, actually, this is kind of neat. So then, and let me put this channel 1 on 2 volts per division. And then let me also temporarily disable channel 1. So then you see the little spikes. The little spikes are like the derivative of the square wave. So capacitive coupling, right? So you remember that the RC circuit, the RC high pass also works as a differentiator. So we're kind of seeing the derivative of the signal. So you kind of, if you see the derivative get through, that kind of tells you there's capacitive coupling between two things that you didn't want to be connected. So you kind of see this signal, this unwanted signal leaking through, but it's not the whole signal, it's like the derivative of the signal. That's usually a sign that there's some capacitive coupling between this signal that you don't want to get through in this place where you don't want to see it. You want them to be not connected, and they're basically not connected, but they're connected like with a little bit of capacitance. And then what gets through is the derivative of that input signal. So that's okay. So that's kind of neat. Okay, so that was part 5 of lab 20, which is basically just asking how good a switch is this DG403 analog switch. It's kind of a like eat your spinach kind of question. The fun stuff is the applications. So part 6. So let's see how that looks.